You guys want to bigger? Get a new stuff. Still in respond. So we have homework 10. Review 23rd, Tuesday. Homework 11 will be due 30th, which is the last week of classes. And there will be a homework 12, which is going to be due, I think I'm not written here. I think it's May 3rd, Friday. End of the day, let's say. Final exam. Amen. Okay, did anyone check this? Do check it, like sometimes.
The exam?
Yeah, the
Yeah.
exam time, you did independently check it, right?
Yes,
Okay, good.
on the web page. It's-
No. On the web page means on the university web page, you mean?
Oh,
No, not on the course web page. So what you do is that, like, I don't get this information. So what you have to do is, based on the class times, university decides when is your exam. So I go to the calendar and check it out, but it's a table. You can make errors. And I have made errors in the past. And then everyone gets confused and it's a mess. So if one of you guys can check it, it's good. Okay. So something about the final exam. So final exam, we agreed was going to be 60% take home.
Time is correct.
Time is correct. And the day,
Yes, it's Thursday, May 9th.
Thursday, 2:45.
Yes.
Okay. Okay. So final exam will be 60% take home plus 40% in class. There will be 5 questions, so there will be 3 questions here. Or this one, I don't know how many questions. This will be 2 questions. So 40% of the grade at least will be on this. Now, it has to be set beforehand as to how I'm going to grade it. Now, if you, most of you have grades below 80 or above 80 as of today in the class out of 100 total. Okay, so I'm going to give a 50% curve parameter. Whatever you lose, I'll put in 50%, which means that you can increase it to 90 immediately. But so overall, what it means is the following. If you can get 80 out of 100, currently, whatever is your grade, after your final exam, which is 20 points worth, put in some grade in there. You already have 60 points in the final exam. So it's only the 40% that you have to really let's say, uncertain about. This one also, that can be an uncertainty if you get it wrong, but mostly when you have it take home, it is okay. So if you have 80 out of 100 after final exam, then you have an A. If by any chance, so some of you have lower scores, and even if you get a full score on this, it cannot be possible. In that case, you need to work for a 40 out of 40 in this, in finals. So either of this, if you get this or this, you get an A. Okay, so it is possible, for all of you, it is possible to get an A, that's what I mean. Okay. In this way of declaring it, my thing is that then it's not in my hands. You are working for it, and I'm not being, let's say, at the worst partial, right? So I'm not biased, or it's not my, or I have less guilt feeling. So if it's not clear, talk to me again, and I can tell you exactly how much you will have to score out of 40 to be able to get this. For most of you, it is easy, like it's not bad at all. Like for some of you, it might be 6 out of 8. By 6 out of 8 means 6 into 5, 6 into 5, 30 out of 40. So you'll have to get 30 points out of 40 to get an 8. So that's the worst that can happen. For some of you who are doing very well, probably 0 out of 40 is sufficient to get. Okay. Does that help properly? Is that clear? If not, meet me. Okay. We were doing Kepler problem. It's about how planets move around sun, or for that matter, stars move around the center of the galaxy, if you want. And in general, heavenly bodies, how they move. It was mostly given by Kepler. Kepler got most of it correct. And it was all experimental based, like Kepler had very good observations from Tycho Brahe, and it was he who mostly gave it. But what Newton did was he gave an equation that governs Kepler's laws of planetary motion. So both Kepler and Newton, or for that matter, that whole set of people, it's a lot of people together get this done, but this, whatever we are studying, can explain that very well. So think of two objects. So let's say this is mass of this could be sun, that's m1, and it has a position r1, and there is another object m2, which no r2. Mass is not a vector. Yeah. So R2, this could be general positions, and we understand that one goes around the other, but we could always ask, what if one of the masses was not very small? Like what if it was exactly the same? Then what will be the motion? If you had two equal masses, let's say Earth was as big as the sun, or sun was as small as Earth, what do you think will be the motion?
So, would be motion, the attraction force between them and cancel each other out?
Yes, no, cancel each other, but then still motion is possible, right? So it will be sort of what happens is that there is, so there is still a center of mass, and there will still be an elliptic motion. But this is the elliptic motion of what? This is an elliptic motion of R1 minus R2. Right, so that's what, so this point, this will be R1 minus R2. That has to satisfy the elliptic motion, but that doesn't mean that M2 is sitting on this orbit or M1 is sitting on. So R1 minus R2, they have to be always opposite to each other, and they will go around. Like think of a binary star. Have you seen motion of a binary star? Sometimes they simulate these things. So one is going, let's say pretend it is a circle, the other one is also going in a circle. So they go in such a way that the distance between them satisfy this equation. So let me write that down few steps and then I'll come back to this. So we have two masses, that's your coordinates. Of course, there are velocities also. And notice this is R1 minus R2 or R2 minus R1, right? So this is R2 minus R1, which we will call this R2 minus R1. We call it R, and there is another point M1 R1 plus M2 R2. That's equal to the center of mass times, for dimensional reasons, M1 plus M2. So that's a definition of the center of mass. First thing you would do is write the Lagrangian in terms of the complete variables, R1, R2, and then the velocity of the first object and the velocity of the second object. And there is no time. This is equal to half M1, let's say V1 square plus half M2, V2 square. And the interaction energy between them is given by Newton's law of gravitation. And that is potential is minus, but you subtract, right? Kinetic energy minus, so it just becomes plus. So it is G M1 M2 over the distance between them. So it's R2 minus R1 or R1 minus R2. It's the magnitude of that comes in. We make the substitution and we learned that this is also, once you write it in terms of the new variables, this is capital R, and then we have to talk about the velocity of the center of mass and the velocity of this R1 minus R2. The difference between the position, the relative position between the masses. That's the velocity associated with it. And here we said this is equal to half m dr by dt square, where m is equal to m1 plus m2. And I'm going to write a reduced mass, which is m1 plus 2. That was a definition, and we showed last time that this is the same as mu r by d square plus g m1 m2 over the magnitude. So when I don't write this vector, so that's the magnitude of this relative distance. And the best thing that happens is that there is no center of mass dependence on that. That means that the force associated with this variable will be 0, which means this is going to remain constant. If it is going to be constant, you can go and sit on that point, sit on the center of mass. So it is constant, velocity is constant, it's going straight somewhere in the user. Go and sit at that point and it is at rest. So you can choose a coordinate system, which is called the center of mass coordinate system, in which this is exactly 0. But you have to choose that. And you can do that only once. If you have 2 galaxies you're working with, and you are also interested in the internal motion, then you can choose one of the center of mass to be the rest, but not the center of mass of the other galaxy, or the whole system has to come into picture. So at least one point you can choose this to be 0. In our case, that is indeed the case. So this can be chosen. So choose your frame so that this is equal to 0. We have still not necessarily specified the origin of our coordinate system. It is only the velocity of the coordinate system we have set. We could still have our origin wherever we want, and we will set our origin later again. So we have that freedom. So once this is gone, this term is gone because of this choice. So we have only one vector to worry about. So earlier we had two vectors. 3 coordinates here, 3 coordinates here, 3 velocity, 3 velocity. So total we are talking about 12 variables we had to worry about. We got rid of 3 plus 3, 6 by judicial choices. So now we still have 3 coordinates and 3 velocities of the relative motion. So that's equal to, let me write that. So this is R, the R by dt is equal to half mu the R by dt square plus G M1 M2 over R. At this stage, let me point out something like, so if you were to write down our equations of motion, I think we did this last time. So P is equal to mu times the R by dt. And the force, if you want, so the force, the generalized force, but in this case it is exactly the force, which is partial derivative of the Lagrangian with respect to R, is equal to, you take the gradient of 1 over R. So d by dr of 1 over R is nothing but the gradient of 1 over R. That is minus 1 over R squared times the gradient of R, chain rule, right? First you take the derivative and then chain rule of R, or the gradient of R is R hat. So it's R hat over R squared. Right? That's how we get the force equation. And that's nothing but minus R hat G M1 M2 over R squared. So our Newton's law or equation of motion will be d square by dt square times R mu here is equal to G or minus R hat times G M1 M2 over R squared. And there was I made a comment last time that if you're doing introductory level physics, then you don't write this mu, right? In introductory level physics, you would say the motion, the one that is moving, which is the earth. So you would say, so let me write that down. So let's call this M, this is less sign, so that's earth. And M greater is sun, let's say. Okay. So we are usually, if we were doing undergraduate physics introductory level, you would say the one that is moving, which is M less times second derivative of the position of earth would be equal to minus R hat G M less M greater over R squared, right? So you would conclude that the mass cancels out. And this is M greater, which is the mass of the sun, over R squared, which is the mass of the sun that comes in, right? There is no appearance of the mass of Earth in here. But that's not completely correct in the sense that now if we were to do it in this way, so this equation here seems to tell you that it is second derivative d squared with respect to R is equal to minus R hat, and you have G over R squared. And then there is M1, M2 over mu. And you would say M1, M2 here. This is M1 plus M2 over M1, M2, which is capital M over M1 times M2. So M1 and M2 seems to be capital M times mu, or M1, M2 divided by mu will be 1 over. This is equal to minus R hat G M over R squared. But M is M1 plus M2, you can write it as G M less plus M greater over R squared. That's the same as. Let me write it as close to possible as this. This is 1 plus r less over r greater. Right, that's the mistake you make if you want, like in introductory level physics, we're missing this. Right, but then you ask, how much is that really equal to? So what is r less over no, what did I write? Mistake, right? M. So m less m greater, okay? So how much is m less over m greater? Earth's mass is about to 2 sig digits, 6.0 into 10 raised to 24 kgs. And mass of sun is about 2.0 into 10 raised to 30 kgs. Right. That's 3.0 into 10 raised to minus 6. That's a number like, it looks like this, 0, 0, 0, 0, 0, 0, 3, right? So only if you were doing a calculation which is precise to 7th significant digit. Is that correct? 1 less than 6. Better? All right. I think so. Okay, sorry. So only if you're doing an experiment to 6th significant digit, not the 7th significant digit, will this really matter. So most of the time we are okay. So there's nothing wrong in it. But in electrostatics, gravity surprisingly has not been let's say experiments in gravity have not been done to 6th significant digit. One of the best experiments done is in St. Louis, WashU, but still I think it only reaches about 4th significant digit or 5th significant digit, and it was realized only in 98 or so. But which field does have accuracy way beyond 6th digit, and that is the 13th significant digit, and that's electrodynamics. And there this really matters. And remember, electrodynamics or electrostatics at least has exactly the same expression. So there you want to keep these. For example, if you're working on a hydrogen atom, then you can do experiments very easily with this accuracy. Okay, so that's a small comment. So we have come to this equation. We still have 3. A vector r here is completely free, right? And most of the time when you look at our planetary motion, it happens in a plane. Like Earth goes in a plane, correct? So it seems like even this is too much. So how do we argue that? So let's look at angular momentum. So angular momentum for the system. This is vector. That's a Lagrangian L, same letter being used. So hopefully it won't be confusing. One always comes with a vector, and if you're writing the components, we'll write z component, x component. So hopefully it won't be confusing. Let's stick to this because this is pretty standard. Lagrangian L is also very standard. The angular momentum is also standard. Let's not change it. So this is r cross p, correct? So how does it change? So we are asking that something is, so Earth and sun is going around or Earth is going around the sun in circles, its angular momentum is expected to be pointing in the plane perpendicular to that. And we are asking, as things are moving, as we are evolving after 20 years or so, does this move around? Does our plane of motion of Earth, does it change around? How we will be able to sense it is that stars will change. The position of the stars will change relative to where we are. And we have written information of about, you can say, even if we go a little beyond, let's say 2,000 years, we have very good written documentation of where the stars were. If you could depend on some diagrams on caves and so on, you can even go behind to 4,000 years, but not more than that. So we really don't know how things happened before. but you can indirectly get some information out of it. So we are asking, is that axis changing or not? But let's see what happens based on our equations. Motion, dl by dt is equal to the r by dt crossed with p. This can hit on both, plus r cross dp by dt, right? And this probably you've seen this in homework at various other places. So this is p is nothing but cross with p is mu times the r by dt, right? So two vectors cross product, that's equal to 0. I did say somewhere that two vectors need not be 0, but that's in quantum mechanics when they're operators. Here, these are simple functions, simple vectors, so this is equal to 0. Say that again?
Simple scalar.
Simple, these are vectors, right? So
Scalar vectors.
or numbers, these are, how do you say this? These are not operators. Like if, for example, operator will be of this form. So L, if you have I hat d by dx, or gradient operator, right? So R crossed with a gradient operator, right? That's what your angular momentum is. This doesn't satisfy necessarily L cross L equal to 0. But if they're simple vectors built out of numbers, so here it is not numbers, right? Here these are operators, right? In that sense, it is not a number, but these are built out of numbers, like velocity is 3 meters per second. Here I'd operate on something and then I get a number, but as such it is not. So this is 0 plus R crossed with, now I don't know what is dp by dt in general, but if we are talking about the momentum of the system, then I know that that's equal to this, right? This was dp by dt, and that's minus r hat g m1 m2 over r square, right? That's a force. Q1. And again, we see r times r hat, that's also equal to 0. So this is equal to 0. Each one is equal to 0. So angular momentum is conserved. That means that once our the way, I mean, historically, our understanding is that a lot of masses, dust started collecting together and they started going around. But whatever that initial collection of dust, that whatever was the angular momentum associated with that, all the velocities added up, that decided in what direction we are going to be facing and the plane of our motion. So this is equal to 0. So L is equal to 0. So there is a vector L which doesn't change. Like all the imagine sun and millions of planets going around, or all the masses going around, and that is a very particular vector which will stay fixed. What about our Earth? If it was just an Earth and Sun system, two mass system, let's also talk about R dotted with L. What is that equal to? So that's R dotted with R cross L, right? The cross product and a dot product. The cross product is always perpendicular to R and T. So this will be always perpendicular to that. So that's equal to 0. What that means is that wherever that object is, right, it will always be perpendicular to that. So this is R1 minus R2, remember, this is vector R. This will always be perpendicular to L. So if like this could be your sun, this could be M1, this could be M2, this is R1 minus R2. Not necessarily the origin is at the axis, R1 minus R2, that's vector R. So this could be R1, that could be R2, they will always be perpendicular to L. Is that clear? If that is perpendicular to L, then choose, right? Choose my L to be equal to Z hat times LZ. So now I'm setting up a coordinate system. Remember, here when I made the choice, this was related to the velocity. I didn't have to fix my axis in any way. So my axis is still free. I can have any axis I want and still have my velocity to be equal to 0. And now I'm rotating my axis and choosing it to be z hat times Lz. And let me also choose, now the vector r in that way would be x times I hat times y times j hat plus z times k hat. Right, so I've chosen my axis to be in the z direction. Now I still have the origin remaining. I say that this orbit is at z equal to 0. So that's a choice I'm making, right? So origin fixing, and first I rotate it to point along the z axis, and then I can move around up and down, and I choose my z axis so that the origin such that z is equal to 0. That just simplifies things. So I have only x and y remaining in the problem. So let's go back and look at this more carefully. So this is x, y, z if you want. X, Y, Z. And let me call it Vx, Vy, Vz. Right, that was your three components. And come back in here. So that's half mu Vx squared plus Vy squared plus Vz squared. And this is plus G M1 M2 over x squared plus y squared. There is no z square, notice, because I've used this to be equal to 0. Okay. So that's the difference that happens in here. So write down equation of motion again. So that is Px is equal to mu times Vx, Py is mu times Vy, Pz is equal to mu times Vz, and force in the x direction, force in the y direction, and force in the z direction is equal to, let's begin with force in the z direction. What is the force in the z direction?
0.
0, very good, because there is no z dependence now, right? That's dl by dz, that's equal to 0, right? That's the advantage we have, so that's why it doesn't drift away, right? Whatever this orbit is, that plane doesn't drift because there is no force acting on that, right? What is fx? It is minus d by dx of g m1 m2 over x squared plus y squared. That we can do. Do you want to evaluate that here? So this is d by dy of g m1 m2 over x squared plus y squared is equal to 0, and this is equal to mu times second derivative of x with dt squared, mu times second derivative of y with dt squared. This is equal to 0. This implies this is equal to mu dz by dt, and let's say this is equal to, that means mu times dz by dt is equal to a constant. So even if, so the whole thing could be drifting upward, that is possible. And again, if oh, I set that to 0. Okay, so why did that show up? Oh, it does. Yeah, so I guess Vz can be constant. Right, if we are drifting in this direction, that's, it will drift with constant velocity. That's possible, but we still can have motion in this direction. We think is fine. Is that correct? Do I get to 0? Yes.
Isn't it 0? Maybe.
Yeah. Why is it 0? Oh, why is it 0? Do you get Vz equal to 0? No, you get second derivative of, so what we get is dvz over dt is equal to 0, right?
Yeah, from R, xi, yj plus ck, if we set z is equal to 0, then to,
Which one?
you said
Sorry.
R, vector R is equal to plus I yj plus pk.
No, right? Coordinate being 0 doesn't mean the velocity is 0, right? Highest point, when we throw a ball up, at the highest point, velocity is 0, but acceleration is not 0. So choice of z, like for velocity, we need the next point also to be 0. So this I can set at one point, right? At one point in time, I can begin from here. But if by any chance there was an initial velocity in that direction, then it will drift. So the whole, but then the drift is for everyone, R1 and R2, both are drifting. The Earth is drifting, Sun is drifting. It's not that we are having a helical orbit of the Earth. The Sun is drifting, Earth is drifting. So for all our purposes, we won't even realize it. Right. So that's why we never consider it. But the way we are doing it, in principle, that could be a drift. Like, but everyone is drifting. The whole system is drifting in that sense. And this is in addition to this drift of the center of mass, I suppose. So I would expect that somehow we can make that choice in such a way that both goes up. But we already set this to 0, so I cannot choose that to 0. Yes. Think about it, because hard problems are for you to do. Right? My question is, the center of mass has a velocity, so we already chose that to 0. Right? Now we are having a velocity of the relative velocities, relative position of the particles, right? And I cannot choose that to 0 because I have already set my coordinate system where that is equal to 0. It seems like I have to live with that, but that's okay. I mean, it's not going to disturb anything that we do from this point on. But my question is it possible to choose that to be 0 somehow? Is that clear, question? Is the question clear?
Choose the,
Is it possible to choose the velocity of the relative position vector to be 0 in the z direction? Yeah. And it doesn't really disturb anything because it just doesn't have any richness in it, just drifts with that feature. So if we live with that, and what we have is basically x, y, and the velocities. So let's go here, and let's.
At the end of the last class,
Uh-huh.
we got this dr by dt as constant,
Capital R.
capital dr by dt.
That's correct.
So this one and this one is not there. This is choice, no? Taking dr by dt here.
dr by dt, the capital dr by dt
Yeah.
is a choice. That's Vx, right? That is Vz, let's say. Vx, capital V, capital Vy, capital Vz. Right? I choose that to 0.
Okay, today.
Okay.
And in the previous class at the end, we found that one as a constant.
Yeah, that was a constant, but then I say that I can choose my frame where this is 0. So I always have the freedom to choose what my frame in a certain sense, right? How fast I'm moving. So what are the choices possible? I can fix my origin. I can set the orientation of my axis, right? Both x, y, and z, and how fast I'm going. All that are choices. I can fix once. So the velocity part, I chose to set this to 0. So now I cannot do that again, because if I set this to 0, then that will get disturbed. So if I set this to 0, that means that our center of mass is going to be going, which is okay, that's perfectly fine. But that drift I'm not able to take away. That's what I was wondering if there is. Maybe this plus this should be set to 0. That's what we should be doing. Somehow we should have, yeah, maybe that's a better thing to do, because now we have a, no, but that has a capital M, right, to associate with it. So we cannot set. Together we cannot, yeah. think about it. Yeah. Again, it doesn't really change the result at all because there is only a drift. Okay? But it will be nice if it is really zero, we have a frame in which it is really zero.
Oh, isn't this the answer we are supposed to give?
There is no supposed to, what do you mean by supposed?
I mean, like you chose that to be zero
Uh-huh,
and you chose the origin z to be zero.
yes.
So you did all that to get that answer or?
No,
get that
no.
outcome?
I just never realized this. I mean, I've done this before. I mean, usually you know that the motion is in the XY plane. So you immediately jump into the XY plane. So you don't highlight this so much. So this, when I was talking and I was highlighting that, oh, where are the approximations made? And we're realizing that, oh, how do I get rid of this now? I don't have to get rid of it, it's just a drift. But then you would always think that whenever there is a drift, it is usually possible to set that to by choice. So, like one argument I can see is that these are two different coordinates, right? R and R. So in a sense, there are two different choices. So these are two coordinate systems. One is for R and one is for small r. So maybe there are two choices there, but I want to be careful so I'm not making that statement. So two coordinates, like it's like saying we started with 6. So in principle, I have 6 choices I can make. So this will be that choice then. So I think that is probably what it is, but I want to be more careful. Okay. Okay, good. Okay, so let's come back to here. So the Lagrangian we have is after I choose my x and y, that's x and y, and then there is dx by dt, dy by dt, and I would like to stop with that, but because of our discussion that just happened, this is still there, but that's not going to be, it's just a constant, it won't affect our discussion at all. So this is equal to half mu, and this is, I'm going to write this as bx square plus by square and bc square.
We can get rid of that, right? Because in Lagrangian, if there's no way, no varying, right? It is
No what?
constant. There's no variation in the c direction velocity. If it is a constant, we remove, like, we don't consider.
Yeah. Correct, we can,
Just
I mean, I can remove it here, you're saying, yes. But my point is that I couldn't, yeah. Or you're saying, no, Lagrangian is not constant, right? Only if it's a position and time dependent, you can remove it.
Oh,
Not velocity dependent, you
Yeah,
cannot
yeah.
remove. Right, if that's the argument, you cannot. Okay, so clear, so the argument was that, oh, you can always get rid of it. RT, any function which is R and T, position and time dependent, you can rid of it. This is velocity. So keep it, it won't hurt. I don't like it, but if I can live with it, you guys can. Okay, so since motion is happening in a plane, so it is good to go into radius cylindrical coordinates r and phi. So choose x square plus y square is equal to r square, and phi is tan inverse of y over x. That's a cylindrical coordinate, and in that case, x is equal to r cosine phi, y is equal to r sine phi, and x dot square plus y dot square. That's the velocity. What is that equal to? We have worked on many Lagrangian problems. What is that equal to for this?
Radius,
X dot square plus y dot square? No?
sine square plus.
And it's
Cosine square.
What is this equal to? Immediately, based on whatever examples you have done in your homework, you should be immediate. R square? No. No, this is R dot dot.
Oh,
No? Okay. Then, huh?
R dot square
Okay, r dot square, yes, that's part of it, and very good,
and bracket for.
very good.
N square. Wait,
Yeah. Tell that, be confident, yeah.
Times square 5 dot.
No. Okay, let's do this. X dot is r dot cosine phi plus phi, right? So this is r phi dot sine phi with the minus sign, right? Y dot is r dot sine phi plus r phi dot cosine phi. X dot square plus y dot square. I have to square this. This square plus this square is r dot square. This plus this is r square phi dot square. Cross terms cancel. That's it. Okay. So this is plus r square phi dot square. In your homework, you use this, or you must have done it, or you have done it.
Yes.
So that's an angle, if you want, this is the angular velocity, right? So this is nothing but v is equal to omega r, right? That is equal to r phi dot, right? R phi dot is nothing but the angular velocity. Let's call that v phi, right? The angular velocity. Okay, so our Lagrangian then is equal to r phi. I can have a velocity with respect to r, so this is dr by dt. And d phi by dt, angular velocity. And there is a dz by dt floating around because I couldn't argue that out. Okay. That's equal to 1/2 mu r dot square plus 1/2 mu r square phi dot square. This is minus g m1 m2 over r, right? Does this depend on phi?
Just find out.
Phi dot, but not phi, right? So it's independent of phi. Right. So we got rid of one more variable. So now we have 1, 2, 3, and dz by dt is floating around. So in principle, there are 3 variables in here. So let's again do equations of motion. Momentum in the radial direction is equal to, and now there is a momentum in the phi direction, right? Or I shouldn't say phi. This is the momentum associated with the radial coordinate. This is the momentum associated with the phi coordinate. So this will be mu and r dot. That's straightforward. That's the velocity. And now we have mu times r square times phi dot. What is that? That should be a familiar.
Alpha. Accelerate alpha.
Alpha, no.
Acceleration.
No. Acceleration will have 2 times, right? There's only 1 time. mr square, what has dimensions? What is mr square in introductory level? Moment of inertia. This is omega, so
Yeah.
moment of inertia, omega,
Angular.
angular momentum, right? So this is the momentum associated with phi. This is a generalized momentum, canonical momentum. This is nothing but angular momentum, right? So let's call it LZ. Or let me keep it P phi actually. Let's also call it LZ. Okay. Yep. So this is nothing but angular momentum, right? Because we are working in a generalized coordinates, it's called momentum, it is canonical momentum. Okay. Oh, what is dl by d phi? 0, right? Perfect. which means that dp phi over dt, that's our Lagrangian, Euler-Lagrange equation, that's equal to 0. This implies that Lz is constant. Right? It should be, because we have Lagrangian, angular momentum was completely in the z direction. Phi is the angle associated with that rotation, so that should be constant. That's what is coming out. That makes sense. R direction is the force in the R direction is equal to, that is R here, so that's minus. Now we are not writing any vectors. This is not a gradient. This is just 1 over R. So it is G M1 M2 over R squared, and that is plus. Is that all? Hmm?
So wait,
No R hat, because this is not gradient, right? This is just 1 over. There is another term, right? This is another time, so I don't worry about that. And that's mu R phi dot square. What is that? That should be familiar again. Mu omega square R and a mass. Omega square R, this is in the introductory level coordinates, notation. What is that? Centripetal force, but usually centripetal force is inward, right? This is outward, so it's centrifugal force, right? This is the origin of the idea of centrifugal force. This is really a force, notice. When we do it in introductory level physics, this comes as an acceleration. Right here, the acceleration is showing up as a force, so it is effectively a force, but it's not really a force. We understand that in introductory level physics, we don't talk about centrifugal force because it's not really a force, it's an acceleration. But here it is an effective force. This is a generalized force, so it is a force, but obviously not in the sense of originating from a mass, but effectively it's a force. So that's a centrifugal force. Okay, so that's good. So we have this as our equation, or our equation. So this implies, right? So this implies that our equation of motion will be, let me write this here. So mu r dot, mu r double dot, acceleration is equal to G M1 M2 over R and plus mu R phi dot square. Oh, thank you. And there is one more thing, that mu R square phi dot is equal to LZ, stays the same, it's fixed, it's constant.
I don't.
No, right? Phi dot. Because I already used that. So this gives you phi double dot here, but that's equal to 0, so LZ is equal to a constant. Okay, good.
In the Lagrangian, the potential term should be plus.
Plus, oh, did I make a mistake? Oh, right, okay, yes, this should be plus, very good. Good. Oh, that's what, it should be minus, right? Then what happens to, yeah. Let's wait, okay.
whenever we started,
This
it
is
was
plus, yes, thank you, this is plus, and then what happens here? Then this becomes minus. This remains the same, okay. Yeah. Force is attractive, yeah, this I should have guessed, right, because this is a force is attractive. This is the centrifugal force, which is the upward. That, okay, interpretation wise, everything is fine, so hopefully all is good. Okay, good. Okay, so this means I can replace phi dot. Okay, so I can replace that, so my equations of motion becomes now single variable, right? Now, eventually, finally, we are in a single parameter. And that helps minus G M1, M2 over R square. And plus mu times R, and this is LZ square over mu R raised to, no, mu square, right? Mu square R raised to 4. Right? That's equal minus G M1, M2 over R square plus LZ square over mu R cube. That's your centrifugal force. Okay, this is the gravitational inward attraction. This is because of angular momentum. If you were not having angular momentum, if you don't have a tangential velocity, then this won't exist. So you have to be moving have to have a circular sense of it for you to be able to balance. So why is Earth, you can say stable? Because it has this angular momentum, LZ, this is balancing this, so there is no tendency for it to accelerate towards the center. That's one interpretation, but in introductory level, for various reasons, we never tell it in this fashion because it is confusing, because there is no such force as an outward force. This is an effective force. Angular momentum is a dynamics or motion related force. It is not originating from.
It's a reaction force to the,
It's not a reaction force, it is a dynamical force, I would say. Reaction force would mean that there is an action. But there is no action for this, right? This is just because the way it is moving. It seems like it wants to go outside, but no one is pulling it outside. It's completely dynamic, right? It's because of the motion. In that sense, it is, that's what usually. Okay, so that's good. So we finally have an equation, so we have to solve it, and I have 10 minutes. Let me try. So let's write this. Remember, if you have a force, if I can write that as a derivative, then I can have an effective potential energy. So can we write this as a derivative? This is, can I write this as a derivative of something? Because acceleration, mass times acceleration is force. If I can write the force as a derivative of something, then I can interpret this as a potential energy. Okay. This is, of course, we know is G M1 M2 over R. So
This should be,
there should be the minus. Right, with a minus, right? So minus minus cancels, and then again minus sign will come out with the derivative. Okay, what about the other one? This will be LZ square, surely exists, mu R square probably, and that is a factor of 2. Because
yeah,
when I take a differentiation of this, minus 2 shows up,
that should be-
and now I have to worry about the sign. Is it correct to say that this is plus? Right, that should be plus. Okay. And this, we know that, yeah, okay, so. Good. Okay. Any questions? Not satisfied?
So here we got rid of VC because we can fix on a plane.
Oh, VZ, where did I? But I could survive without it, right? Sure. Okay, let me see. So there's a PZ you're saying, correct?
Yeah.
This is mu times V Z dot. Correct? And I will still have this dl by dz is equal to 0. And I will have dpz over dt, that's what we said there, that's equal to 0. This implies pz is equal to a constant. So how does this go in there? Yeah, I don't worry about it. Let's stick it. Who cares? Right? I was only working with this equation, right? The radial equation, I used the phi hat in this, and I got this equation. This is my radial equation. Now this whole thing is moving, I agree, right? But who cares?
So now still
Uh-huh.
in L, it should appear the half mu c dot square.
No, this one,
L.
Yes.
The second,
angular moment. No, this is,
The-
and zero
the
moment.
second equation above.
Lagrangian equation. The above, this, yeah.
Yeah, the
The
below,
next one.
L, yeah,
Yeah.
in that one.
Yes, I agree. So this should have been mu 1/2 mu z dot square. Accepted. Perfect, yeah. But doesn't affect my conclusions. I don't affect my conclusions, but then I had to fight with Newton. So, no, okay, so I don't want to contradict Newton. Okay, good. With me? Okay, thank you. Okay, good, good corrections, yeah, okay. So, we have, let me rearrange this somehow, so this is equal to, so I'm going to do some manipulations. I'm going to multiply by R dot. Right? This is standard manipulations that you do in undergraduate physics also, when you do work energy theorem. By dt times minus g m1 m2 over r plus 1/2 lz square over mu r square. Okay. And I will do the same thing on the right, right? So this is equal to, let me do that here and next one, right? dr, let me write it as r dot, that way it is easier to see, I think. This is dr dot by dt. Like second acceleration is velocity over time. I multiplied by dr by dt, so that's a dr by dt.
Should be in the last.
Okay. Mu, good point. Okay. Let me. Right. But if you think of derivations of kinetic energy in your introductory level physics, that's nothing but kinetic energy, right? So it is d by dt of half mu r dot square. When I take a differentiation, mu r dot and then double dot, right? So that's this. So that's a kinetic energy. That's how you, if you recall your introductory level kinetic energy, where it comes in. That's what you do. This is a chain rule. There is only one variable, so I can get rid of my r. So it is basically time derivative there. So what I have is time derivative of kinetic energy plus potential energy is zero. Did I do this correct? Yeah. Like this is the gravitational potential energy, and this is the, if you want rotational potential, rotational kinetic energy. So this is the rotational kinetic energy. This is the radial kinetic energy, and this is the gravitation. This is equal to zero. If something is derivative is zero, that should be a constant. That's energy this, right? So we have energy of the system, which is constant, which is again not surprising. So we have 1/2. Now finish this. 3 minutes. Minus g m1 m2 over r plus lz square over mu r square 1/2. Remember, this is angular momentum over moment of inertia, right? That's the kinetic energy associated with rotation. So that's equal to energy which is fixed, which is constant. Interpretation, this is radial kinetic energy. This is rotational kinetic energy. Rotational in the sense of phi direction rotation, rotational kinetic energy, which I'm interpreting here as a part of potential energy. This is gravitational potential. Take 5 minutes extra, which I've been doing. Okay, so we are interested in R the time, so this is the same as dr by dt. I'm going to do a few things, multiply by 2 everywhere. And and what? Yeah, and divide by mu, so it's 2 over mu square root of E plus minus of LV square with me. What are we interested in? This is position as a function of time. Correct? We also have recall mu r square phi dot is equal to LZ. That means d phi is equal to LZ over mu r square times dt. So angle is dependent on time. So I can replace time with angles, which is not surprising for us because how do we measure our lifetime? We go by age, right? Age is how many years has Earth gone around the sun? That's angle. Right? When we say we are 27-year-old, we say the Earth has gone around the sun 27 times and 3 months. That's angles. Right? So anything that is monotonic in time can also be used as time. So why not angle? So instead of time, we are going to talk in terms of angle, which is good because we will want to write position as a function of angle. Like that's the orbit. So if I replace this, I get a something in terms of phi, and then if I integrate that, that will be my orbit. So my strategy will be replace t, so put it
So why 2 over mu is out of square root?
out of square root. Why is it outside square root? Because it's a mistake.
Inside.
It's a mistake, I suppose. Thank you. So distracted. Again, so to avoid that distraction, so we have this as our equation. If I integrate this, I get r as a function of time. So that's good, but what we would like to do is do r as a function of angle. So what I'm going to do is first replace dt with d phi, so which can be done immediately. So this will be mu r square. So dt is 1 over dt, right? Oh, so this LZ over mu r square times dr over d phi would be equal to 2 mu energy plus g m1 m2. Six. This is, we will show that this is doable because d phi, if you separate separation of variables, gives you 1 over 2 over mu energy plus g m1 m2 over r minus and z square over 2 mu r square, and then a square root. All the r's is on the right. All the phi is on the left. Phi integral is trivial. So integrate both sides. If I can integrate this, I'm good. Okay. And we'll show that that's a very straightforward, simple integral. It's just a matter of moving things around. There are too many variables. But that's just a trivial integral that we see in undergraduate mathematics, calculus, and we will show that this is ellipse. This will be giving us an equation of an ellipse. I would like to finish that, but we will move it to the next one. Quiz. What is the equation of an ellipse? Not in rectangular coordinates, in polar coordinates. What is the equation of an ellipse in rectangular coordinates?
Right limits,
Huh?
right limits.
That's a straight line. Ellipse. In rectangular coordinates, what is the equation of an ellipse? You guys know. What is the equation of a circle? Let's begin with this. X square plus y square is equal to r square, right? That's the equation of a circle. What's the equation of an ellipse? Ellipse is very close to a circle, right? If you squeeze the circle, it becomes an ellipse.
Like x minus.
X squared over A.
Yeah, good.
And plus y squared over B,
Very good.
and plus z squared over C.
That's the equation of an ellipse, but this is in rectangular coordinates. The quiz is,
Put it in.
what is the, put it in polar coordinates, but look it up, that's sufficient to me. Yeah, if you can derive it, that's perfect. Starting from here, get that, but there is a catch in there because the r theta, r and phi has to be, so here the center is in here, right? So when you do this, this is your r, and that's your angle phi. So this origin is shifted a little, so it is not easy to directly get it from here. That's almost 10 minutes. Thank you.